Fine. For now, this is the promotion. And without wasting further ado, I would like to now invite Carl from AWS team to share more insights on GenAI and EKS and all the fancy stuff. Thank you so much. Over to Carl.
Fancy stuff. Yeah. Just hang with us for a minute while we bring this up.
Awesome.
It is an absolute delight to be here again. In fact, I'm with you all every month, but on this side to talk to you this time about Gen AI and how we're seeing this unfold in regards to containers and Kubernetes. And as we have it, Gen AI has pretty much taken our imagination by storm. It's able to generate videos, images, content, even write code. I believe every one of us here in the room today has had several conversations, be it with colleagues at work or even building products around GenAI and trying to get them to market quickly. So in the next 25, 30 minutes or so, I'll be walking you through what we're seeing in industry in terms of how containers are driving the adoption of GenAI, how it's powering this momentum, and a lot of interesting facts to share with you all. In the process, if there's something you would like to ask or share or talk about your experience, feel free to do so. It's a very engaging and learning way to do that for us, all of us. So my name is Carl Varia. I'm the application modernization go-to-market specialist. I work with Matt at the back, who will be coming on to give you a phenomenal demo on this. So this is super interesting and it helps make things real. Together, we help our Canadian customers modernize on AWS. So with that, let's get going into the presentation. And the first topic we want to basically cover is to kind of set the foundation on defining certain terminologies around AI and specifically what are the different topics under it. So first, of course, we have artificial intelligence, which is basically, as we know, the ability of a computer to be able to mimic human intelligence by employing a different variety range of algorithms. Machine learning, pretty much, as we know, is a subset of AI. So all of us are pretty much consumers of machine learning to a great extent, be it when you're watching Netflix or purchasing a product on Amazon, you're recommended with the next best thing to purchase. Deep learning is a further subset of machine learning where you're employing neural network techniques to be able to, let's say, perform more advanced tasks like speech recognition or facial recognition analysis. And finally, generative AI that we're discussing about today is being able to generate new content from learning of the wide variety of data that is there out there. This is an important statistic because at Amazon, we're all about numbers. Gartner predicts that by 2026, 85% of the more than 80% of the enterprises will be using GenAI through APIs or enterprise applications. Just let that sink in because over the next 16 months or about that time frame, we're able to see even greater adoption of this technology at a pace that we've never seen before. So every one of us in different ways or shape or form will be or are being impacted by it, mostly positively, I hope. So kind of putting things into context, right? What has changed between the way we train ML models versus on the right-hand side that you see foundation models? So before I kind of go down this path, just to show up hands in the room out here, anybody who's trained an ML model, maybe at your university, maybe in production or at your work, great. So I see you. Wow, awesome, right? So for all of us out here today to kind of set that base, with a traditional ML model, let's say we take a data set, we need to spend time in making sure that we're able to label it, clean it. A lot of time goes in cleaning the data set. We take it, we divide it into, let's say, 80, 20, 70, 30, where we use most of it for training, the remaining for testing. And then that process goes on, you iterate. So Traditional ML models are great at doing one specific task. For example, churn prediction, fraud prevention, specific data on which it's trained, and then they run. Foundational models are fundamentally different because they're trained on vast amounts of internet scale data. So they're good at several things, but if you want them to be good at a particular thing, they need something called as fine tuning. That's where you provide specific domain-related data sets on which they are further fine-tuned so they get good at those specific tasks. And these differences and nuances are important for us as platform engineers, DevOps experts, or those operating in this field because they have an impact on non-functional requirements like scalability, performance, cost. These things are heavily dictated by the very nature in which these models are being trained and built. So what's really led to this tipping point? There are three factors that have come in together, which is why we are seeing this and experiencing this explosion today. One, over the past few decades, we've had a massive explosion of data available through the web, be it on Wiki, Reddit, or large amount of open source data that's available for us to kind of analyze and learn on. Availability of virtually unlimited compute provided by the cloud, and that overlaid with machine learning advancements that are then able to drive insights into data at massive scale. Specifically around use cases, we see a variety of different applications across different lines of businesses. So for example, in the first one, it's around enhancing customer experience. That's where we see most industries as well as large enterprises looking at application of GenAI to really enhance their customer experience. This could be in the form of virtual assistants, chatbots, or call centers that are powered by GenAI. And that links closely to boosting employee productivity. So imagine an employee sitting in a call center for an insurance organization and we call up as customers, we want to know about our policies. Those models are specifically trained so that they're able to give a very contextualized response to aid the agent in providing a faster time to resolution. So those are some of the KPIs that are being measured at the back to ensure that these are sustainable ways in which you're enhancing employee productivity and boosting the way you provide a superior customer experience. Creative content we've all experienced. All of us are using some form of a GPT to be able to carve out interesting content, summarize notes for us, or just simply make our life easy. And finally, improving business operations, because this is where an example of cybersecurity. We recently published a blog where we spoke about how can you use GenAI to detect CVEs early in your CI pipeline. So it's a very assisted way of getting to remediating CVEs quickly. Now, anybody over here that can tell me what's common across these three applications? Let's just see some similarity that strikes across this. Sorry. Yes, awesome. Thank you. Sorry, no separate price for that, but probably afterwards we'll catch up. But this is good. So these all are great at generating images from natural language. So a little bit of a game, right? Can you tell me which of these images is real, which of these is generated? Okay, show of hands, left-hand side is real. Come on, folks. Left-hand side is real. That's it, 3 people. Right-hand side is real. Wow, not bad. Okay. So the left-hand side is an image generated with that specific prompt or input that specifically says that, hey, generate an image for me with a waffle. But if you can see, we've come a phenomenally long way in making this extremely real, right? So let's kind of get a bit more serious and start looking at peeling the onion here. What are the different personas that we end up seeing out there who we speak to and understand in this ecosystem? So at the very top are consumers. These are basically buyers of GenAI models. They are concerned with making sure that they are able to access the output of the model in the most cost-efficient manner possible with the highest performance. Lowest cost goes without saying, but at the same time, highly performant, right? And for them, it's all about making sure that they are able to then innovate on top of that by providing their context to it. So they are the ones who would like to then fine tune this further with their domain context, be it in banking, financial services, travel and hospitality, or whatever industry there is. The next set are the tuners. These are the ones who are basically SaaS providers of these platforms that are providing models that have been pre-built but trained to specific industries where they expertise in. And finally, we have the builders or the providers. Those are actually building the GenAI or the foundation models from the grounds up. And they become the providers to the upper layers as we see here. So consumers are customers of builders and providers. And these are all contexts for us to keep in mind, because as you stand up your containers platform, it goes well beyond transactional applications that we are used to building, because it extends to the data ecosystem and the GenAI models that we'll see in the subsequent slides. All right, so far so good. These are just some overarching views and opinions on how this thing is shaping up. Now we'll kind of double click into specifically why machine learning on Kubernetes. And for that, we need to understand what are the needs of those data engineers, ML ops, or data scientist folks who are trying to build these models. And what is it that we need to be catering to when we stand up these enterprise-grade platforms? First is dependency management. We all know containers are able to manage dependencies really well. So similarly, when you pick up a framework, be it PyTorch or be it some Panda or some other library, containers are able to package those up just like you would in an application, its dependencies, its configuration, the code. Similarly, would have a model, its framework, its libraries, and that dependency management gets kind of handled pretty well in a container. The second one is foundational models like we saw earlier. They need to be trained on massive data as quickly as possible, requiring you to have compute GPUs available quickly to scale to that demand and then size down once the training is done. So you need some form of ability to orchestrate. So you see there are parallels already emerging from these needs to the Kubernetes ecosystem or the world, because we're already dealing with these challenges on the application side. So the idea here is how do you extend that into the data, the GenAI world. Integrations and security compliance. Moving away from the core technical aspects, a lot of customers and enterprises are looking at how do you make sure that these compute or GPU resources being scarce, how are they made available to all of these different teams? They can share them effectively, and making sure that while they're sharing, each of their respective usage is aligned, or only those people in that particular team are able to access it effectively. So those are some security protocols on top of it. So something like namespaces comes to mind. And finally, you have speed to market, of course. So how do you then quickly, rather than spending too much time on handling something we call as infrastructure primitives? So you don't have to manage those multiple compute nodes. You don't have to manage the dependencies and so on. How do you push that away into something that manages all of this for you while you focus on model building? And that is what Kubernetes was effectively built for. And that's why Kubernetes makes a great candidate for machine learning workloads to run on top of. And this kind of gives like a deeper view, right? Just like I was talking about how a container is able to encapsulate all of these different dependencies. So you are able to basically take all of that configuration, wrap it all up, and then be able to deploy it and effectively orchestrate it across your different compute instance types. And that's really the reason why Kubernetes lends itself to a very effective way to scale. And also to a greater extent, when you're looking at managed services, that makes it all the more better, because now you are not managing the Kubernetes orchestrator. You're not managing the etcd node scaling, the API servers. That's all taken away from you. And that becomes extremely critical when you're handling huge scale work, large scale workloads. Resource utilization, of course, is highly improved, because now you're able to also tell that, hey, this particular team has access to this much amount of compute resources at max. So you're able to pretty much allocate or apportion how much each team consumes. Org standardization, great point. Like I was talking about earlier, a lot of you already today, whether in your respective organizations or what you may have experienced, organizations have stood up their container platforms. They have built their specific tooling onto it. They have something available today. They don't have to start from scratch. they need to extend that further. And finally, open source community, because there's such a strong open source followership or community that's available, that's actually building so many innovations. You can use this open source innovation that's happening at bleeding edge and that bring that into the data ecosystem. So this is what like a blueprint would look like for a Kubernetes platform that's running in any enterprise or anywhere for that matter of fact, be it at the edge, be it on the cloud. At the very bottom, you have the specific environment. On top of that, you have, of course, your primitives, which is the compute, network, storage, security. And then the organization builds their respective service catalog, performs their version controlling, does observability, logging, monitoring, tracing, and so on. Now, on top of this is where the interesting stuff happens for the application developers, because they are the ones who are deploying to this platform. So all of these different capabilities around release, control management, all of this is built in over the work that has been done to stand up this platform. And so it makes sense to build on top of this rather than standing up something net new. Now, in terms of EKS particularly, because earlier we were talking more around the Kubernetes side of the house. So when you're looking at a managed Kubernetes service, the way we've been thinking about this is there are two main stages almost in the entire life cycle. One is the training. Sorry, thanks. One is the training, the other is the inference. So when you're training the model, an important aspect to it is, like I mentioned, the scaling. Why is that? Because you're trying to scale to the amount of data that's being brought to the different compute nodes. So you, especially model builders that are building multi-billion parameter models, are using thousands, if not hundreds of nodes. And so you need to be able to scale to accommodate for that level of model training. And the control plane needs to scale because that's where you're orchestrating your containers. You need to be able to distribute the load across, because it's not just one VM or one big, massive, giant server that's being used to train. And so you need to be able to make sure that it's being able to distribute, get the data back in, and provide this in a very quick manner and manage failures, because when you're looking at that scale, you want to make sure that you can quickly overcome those failures. So what are some of the things that EKS brings to the table, as a matter of fact? So one is, of course, the control plane auto scaling that's completely transparent to those using EKS. But there are other aspects to it, like EKS accelerated AMIs, for example, for NVIDIA or for specific Trainium or inferential. So those are basically custom chips that are helping build and inference and train those models quickly. There's something called as deep learning containers. So those are pre-built containers with machine learning frameworks available for you. So you can just take them and deploy them and run them and work with them. So it really helps you accelerate the build stage. From a storage perspective, while the container itself is stateless, you need to be able to write to a common file system because your model is consistently training. For that purpose, you need a very high throughput, low latency file system underneath it that's powering multiple containers. So for that, we have something called as a K8SUG, which basically provides that capability for models to be able to work at a large scale to quickly write and read from and reduce as much latency there is while going from the compute to the storage layer. And finally, networking. Because you have hundreds or maybe even thousands of nodes, these nodes talk to each other and there's a lot of inter-node chatter. For that purpose, you need to have a network that can sustain a high-performing compute workload. And that's why you need something called as an EFA or an elastic fabric adapter that enables you to bring that on-premise high-performance workload kind of nature in the cloud. And that's what this enables you to do. So remember always, it's across compute, networking, storage, all of these need to come together and work together to provide that scale level of model building and inferencing. And that is where EKS really shines, because these elements or capabilities have been thought through and are delivered out of the box as we speak. So that was all around training. Now we go to inferencing. So imagine you've taken your model, trained it. Now you want to take it into production. So that's when the model starts to inference. And before I get into the inferencing, just raise your hands or somebody could shout out here. how many parameters do you think an average model has today? Or what's the largest model? How many parameters? Can you, some number? Sorry? Yeah, about that. That's right. So you're already going into the trillion. Just to give an aspect, at 2019, the BERT model had about 320 million parameters. We are at over a trillion. That's, you can't even kind of put that into perspective in your head in terms of how much data that is. So that's just the whole training piece. Now comes inferencing. So it's not every time that you train a model that it's successful. There are a few out of maybe hundreds of those that get trained, but those that are successful get adopted very, very quickly. So adoption, of course, again, drives scale, but it's a different type of scaling. It's not scaling where you're basically trying to accommodate all of that data that you're training against. This scaling is for transactions, the user traffic that comes in. Inference models will typically sit between the user sending a request and the model providing a response, right? So that's the inferencing that's happening. So you need to have a very highly performant model. That's why we are always talking about, it's not just how many parameters a model has that makes it powerful. It's also how lightweight or effective is it in terms of cost performance, because these are equally important when you're running it in production. Otherwise, sustaining a model that's going to cost you more than the revenue that you get is not something that any business can run in the long run. So of course, from a performance perspective, like I said, it needs to be highly performant, and cost is always on top of mind for anybody that's running these models, because these are very compute intensive workloads. And in the full life cycle of a model, typically 10% goes to training, 90% goes to inference. That's how much of cost or performance aspects that are important when we talk about inferencing of models. So really to kind of address those scaling cost performance challenges, we have an open source autoscaler, which is Carpenter, that AWS open source. Very, very interesting project. Matt will be speaking in greater detail about this, on how it is able to rapidly provision the nodes as and when required. It speaks directly to the EC2 Fleet API so that it can instantly initiate those nodes as compared to Cluster Autoscaler in a matter of seconds. So that's why it's able to really shine in the way it provisions those nodes quickly and provides those capabilities from a scaling perspective. More on that in the next demo time that we'll check it out. So in terms of running these workloads on EKS, Kubernetes was never built to provide a machine learning based experience, as I've mentioned before. But we need to keep in mind that the users of the platform, the data scientists, are not the ones who are going to get hassled with how do I configure my cluster autoscaler, how do I manage HPA, how do I do observability. They don't want to be hassled with that. They want to use the tools they are familiar with so that they can then effectively work on doing what they do best, which is building models and making sure that the algorithms work well. So for that purpose, the approach here is at the bottom, you have a container platform that's powered by EKS. So you have your typical capabilities around observability, scaling, networking, all of that already taken care of or built. But on top of that, you add the open source tooling. And this tooling provides capabilities around, for example, bringing in the right frameworks to build your ML model, looking at how do you then train it, how do you make sure you have a registry of all those different models, maintaining versioning, all of those things that typically data scientists are well versed with using their own notebooks, etc., things that are familiar to them. So imagine it to be a layer on top of the existing platform so that it extends and provides the required environment in which data scientists can operate effectively. And so that's theory. This is practical. So how do you realize that earlier slide that we showcased? There's something called, as we call it, the JARC stack that's emerging and that we see a lot of folks use out there. So JARC basically stands for Jupyter, Argo, Ray on Kubernetes. Jupyter are your Jupyter notebooks that data scientists are very familiar with using. Argo workflows enables you to really perform your CI/CD with those particular models. Ray helps you to distribute that modeling because ultimately you need a distributed way of training those models, and ultimately all of that is on Kubernetes. Now, how do we help folks like you take this from a slide and run it? That's where we have something called at the Data on EKS initiative that we started late 2022. So this is where we take all of your blueprints. You can take a Terraform apply plug and just do it and run the whole job stack in your AWS environment, for example. So we've made standing up the stack very simple because there are already templates available for you on this website that you can visit. It has best practices. It has running Spark on Kubernetes and different frameworks. How do you bring all of this together? So this is a real good one-stop shop to kind of get you up to speed on how to stand up a Kubernetes framework along with the required data tooling where you can then run your models and train them and then inference on them. And yeah, sure. Yeah, nothing silly. Go ahead.
So when you say this, the models that you are creating out in this one,
yeah,
there are two questions actually. Why we need these big models and then fine tune it for a very specific purpose? Why can't we just build or take part of it and just use it for, let's say, for insurance or for planning? That's one.
Yes.
Second thing is when we say these models train on Kubernetes. So how many parts of Kubernetes are we talking about here? Because this one single.
Yeah.
Maybe I don't know.
No, great. No, absolutely. Awesome. So first point, very interesting first question. So I'll repeat it. The question was, since we have multi-billion or trillion parameter models, why can't we simply just use them out of the box as is for these use cases like insurance or travel hospitality or mining or some other sector? So basically, these models are trained on data that's openly available on the web. Contextualize information. Let's say, for example, there is a particular IFRS standard or a particular way in which an agent has to bind a policy when you ask for it.
So how different?
Yeah.
So these models are trained that huge amount of data that particular use case will not require. That's why you fine tune it, right? So why not rebuild that model just for the data required for that specific purpose?
So then it's the second use case, the fine-tune model builders use case. You saw the one in the middle. Those are the ones who are providing you industry-aligned models. You don't have to go to those big ones then. So you can leave those out of the picture. So there are different, and that's where it comes to this slide exactly here. So there are different players in the market here, and these are the ones that are working with AWS out here. So for example, there are folks who are providing you a platform as a service. So end to end, you don't want to worry about how do you train it, how do you set up all of these different components together. You want a SaaS-based service, and you want to basically provide your data to it so it contextualizes the response. These folks are great at that. Up here is the ones who are providing you with those multi-billion parameter models, and they are the ones who are essentially building it from the grounds up. To your second point, how many pods? Even we wouldn't know, because all we can say is this could be hundreds or thousands of GPUs, let alone pods. So how many pods is a pretty tough one to kind of give a response to, because it also depends on, there are different variants of each model, right? Like some models come with 70B, which is 70 billion, some with 406B. So they actually mention how many parameters. Based on how many parameters will dictate how much infrastructure you would need, because the amount of data you're training it on varies. So it all depends on what is the model being built for. Again, in addition, is it a natural language to image generation? Is it text summarization? What are some of those use cases? Because not every model, for example, is multimodal. So what are the use cases that determines your underlying need for the infrastructure, and therefore how many pods that are required? So how many pods, in fact, should be transparent to you, because that is a primitive that Kubernetes should be handling for you, right? But to your earlier point, again, there are different players that are coming up with specific models then aligned to that industry. So you don't have to hassle with a multi-billion parameter model, because even running those takes up way too much of cost. It's not environmentally sustainable a lot of times because it's taking up so much compute. But then there are again use cases for that. So it all depends on what is being targeted as that use case, and then what was it built for. But great question, and highly debatable. So thank you. And finally, yeah, go ahead. Go for it.
I also wanted to ask, so we know that we need GPU compute resources to train models, right? And it's like expensive and we do all of it. But we use the models. Do we also need GPU, or we can just infer models on a traditional?
So inferencing, that's where at AWS we have a differentiation between training and inferencing. We call it the trainium chips and the inferentia chips. And why we do this is because the requirements of training a model fundamentally differ from inferencing of a model. And so when it comes to inferencing, your response time to provide once an input is given to a model, those matter highly. Versus in the training, what matters is for you to be able to accommodate as much compute to crunch the numbers and provide the output in a definitive time that the model is trained. So to your question, it actually varies all the way down to the silicon level. But yes, there is that element of graphical process acceleration required to be able to provide a very highly performant model response. But that is why when we are developing that silicon, it's actually different between training and inferencing. So you can actually once train, then move that model over and deploy it into an inferencing chip that provides that level of response that's required. Hope that answers there.
Yep.
Questions? Great ones. Yeah, go for it.
So these models require a lot of graphics power to run, right?
Mm-hmm.
So companies like Google and Apple, they say that our models will be able to run on the latest ones.
Yes.
What change are they doing that reduces your cost from, let's say, $1 million to like $1,000? So
That again, okay, method, I am not the person to, if anybody else knows the method, you're absolutely, please feel free to chime in. I'm not the only person who's kind of having this info, but the point here is whatever's going on to those devices at the arm level on your phones, those are very, very, very highly optimized for specific use cases or tasks, which you would otherwise not be able to use for achieving what you would do with a typical GPT-based model, which is general across the different capabilities. So from, like, for example, today, you could ask a model to summarize the text, convert it to image, create a video, generate a song. The FM underneath is not really changing. Although you could, but there is no need because a single FM is able to give you all of those capabilities. The ones that are moving on to devices have very specific mobility-based use cases, which do not need you to have that kind of high compute power required at every device, by every device. So, and also the way they're doing it is pretty cool, right? Because ultimately they are leveraging the number of cores and the amount of compute you have, which honestly the phone never used. For most, it's like having a massive server that you use every day, but you probably use 15% of the capability, right? Or 50% of compute. So they are uniquely positioning to have those models running at the edge. But the purpose for which they are built is very, very, let me put this, very purpose-built use cases cannot be compared to the ones that we find for the wider web consumption. But anybody else here knows better. I'm open to learning as well. I'm open to be corrected. So please, we are all learning here. Let us know, right? Awesome. So we're pretty much over time and at time here. So in terms of diving deeper, now I'll have Matt come over and talk to us something about even more interesting with Carpenter and demos. So Matt, over to you. Thank you so much.
Yeah, while you come here. Oh, the slides are on? Yeah. Okay.
You want to?
Well, I'll use my computer for the demo, but I can use the slides.
Yeah, it's already.
Oh, yeah.
I need to keep switching.
No, but I'll switch ones in 3 minutes. All right, so nice to meet you. For those that missed my name at the start, I'm Matt Bruno, I'm a container specialist at working for AWS. Who's familiar with Jupyter? We talked about in the previous slides. Okay, so I'll be jumping a Jupyter notebook, in a couple of minutes. So if you're lost, think of Jupyter as a terminal that gives you a little bit more tooling into running commands on the host. I suppose since we're in a Kubernetes user group, everybody's familiar with terminal. So allows you to write basically often Python codes to do stuff in the backend, and I will be using that. So, sorry, slides. All right. So the first thing so this is the architecture of the demo I'll be using. And the reason I was asking about Jupyter is because I'll be logging into a Jupyter Hub. What is interesting about the Jupyter Hub is it can provision Jupyter Notebook inside of pods on demand. And in my case, I'm warming up because I'm spinning up a GPU instance behind the scene by using what we call Carpenter. If you're not familiar with Carpenter, this is kind of a it's a version of a cluster autoscaler that was built, that was open source by AWS, and think of it as exactly the same thing. It will be able to spin up your cluster, add nodes to your cluster, and interestingly, it doesn't have the concept of groups, of autoscaling groups, right? So it can spin up instances of different sizes, different types. Can use on-demand, Spot, for example, and a bunch of other interesting functionality. But think of it as a cluster autoscaler for your cluster. So what we'll do is inside of our Jupyter Hub, we'll basically prepare a model, we'll launch a training of it, and we'll see new instance come up. We were using what we call the array cluster that Carl talked about to launch that training job. The training job will, at the end, we'll fine tune the model and put basically what we call the checkpoint inside of S3. So the simple storage service of Amazon, where we can basically an object storage where we can put all the files. From there, if we have enough time, we will basically try to launch, well, we can use it locally, test it or model locally. That's probably where the demo ends. But if we have time, I have also it running as a service job, basically an API that you can call afterwards for any of the customers that may require your fine-tune model. So so that was the first slides. Kubernetes architecture, very high level view into an EKS flavor. As you can see, we can mix the on-demand and the Spot instance. The other thing, so Carpenter is actually the scaler. So it works exactly the same way as cluster autoscaler, right? If you have pending pods, it will basically kick in. There's a 10-second loop, just like an autoscaler, that decides what type of nodes to assign. What's really interesting is it can adjust node size, node type based off the constraint of the different pods that are pending in your cluster. And to do so, you define what we call node pools. So in the current clusters I have two node pools. One is for CPU tasks, and the other one is for tasks that needs GPUs. So just by a couple of lines, you can actually define this and make sure it's cost optimized, and you can shut down those nodes when you're done with your training and stuff like this. I think that was the last slide. Yes, perfect. Let me just switch computer around. This. Just mute your Zoom. Just move the bar around. Oh, do we have yeah, let me just use those mics. Sorry. Oh. Can you hear me, Corey? Okay. Sorry, let me move this around. Again, probably minimize. All right, perfect. All right, so let's start by familiar territory for everybody, right? Oh, sure. Anybody need glasses still? All right, familiar territory. So let's start with get nodes, right? So I have about 5 nodes in my cluster, not about 5 nodes, no, 6 nodes if I count right. You see there's some about 14 minutes, 52 minutes. Those nodes are actually GPU nodes that I just prepped before the demo, but we will be adding some, right? So if we look at the actual pods in the cluster, I'm running a bunch of different things. Very interestingly, so like I said, the Jupyter Hub is running as its own namespace. I do have a Carpenter deployment running with 2 replicas, like best practices say to do so. A bunch of NVIDIA feature for GPUs, we kind of need this, you know, obviously. And I have my array cluster. As you can see, about 15 minutes, I did start a specific model. You know, if we have time for this, we'll see if we can use it. So at that point, basically, I'll come into my Jupyter notebook. This is actually what a Jupyter notebook looks like. And we'll be looking at using BERT, one of the models that Carl spoke about, to see if we can tweak a little bit of, you know, reviews. Like, let's say we're doing Yelp review, right? Is this a fake user? Did he really went over there? Was he mad? Was he good? You know, getting some kind of sentiment over what he actually said. So I should have installed already the dependencies. So let's just see if a GPU is available in my instance. So as you can see, I'm running a NVIDIA 8NG. If you have one of those at home, you're very lucky. You know, I'm just using a bunch of Python codes here, creating a small training scripts. And basically, I will import that into S3 bucket, and I will launch what we call a Ray job at this point. So already have my Ray dashboards here. As we can see, the Ray job is actually starting up. But since we're interested in what's happening in Kubernetes, we will come here and basically check the pods, right? As we can see, we have 2 pods that are actually started for our training session. You know, I'm sure you're interested into how Carpenter actually works in the scene, behind the scenes for this. So I did open up the log of Carpenter. As you can see here, 5256. So it did, you know, it just started doing his work. Basically, oh, I found a couple of provisioning pods, right? We can see here actually, let me try to, I think this will give us a little bit of color. Nice. Right? So as you can see, it created 2 node claim into the GPU Carpenter node pool. So we can, you know, if somebody's interested, I can definitely go in there. Those are actually G5 4x large instance. Actually, I'm sorry, it did say I can use 4XL or 8XL's size of instance, right? So it did that. So that's how Carpenter can actually use different size of instance. Mine is actually asking for spot capacity. So it's passing the maximum amount of different instances that can fulfill that role. And what we call the EC2 Fleet API basically will send it what he thinks is the best option for whatever it requires, taking into account pricing as well as what we called interruption capacity. So to make sure your spot instance will not be interrupted in the next few minutes. So at that point, you see launch node claims. So the API actually answered. So at this point, we know it's a G5 4x hell coming up. And we also have the instance ID. So as you can see, there's a bunch of different things happening. So if we go back here at this point, you know, or not, or nodes are actually ready. So if I do nodes again, we can see we have 2 new nodes, one at 42 seconds, one at 45 seconds. So the nodes are ready, and you know the pods are getting assigned to them. It'll take a minute or 2. The pods are not too small. So that's at this point, you know, if we go check the Ray dashboards, we can see the job is kind of waiting for scheduling. Sorry about that. It will have all the logs in here. You know, it gives us a little bit of warning, but basically saying if you're using cluster auto scaling, it's maybe normal that your pods take a little bit more than 60 seconds to start, right? So let's just wait a little bit for this. If you have any question while we do this, we have a minute to fill. two questions. All right. Go for it.
Okay, how does pricing work for carpenter, or
Sorry, repeat that.
how does pricing work for carpenter?
Carpenter is free. It's a
The resources that it is automatically allocating.
right. So you'll pay for the nodes that Carpenter brings up, right? Right. There's no Carpenter is open source. It's free, just like Kubernetes. You can install it wherever you want. You know,
But it's doing automatically, right? I'm not doing it. So whatever it builds out, that will be the cost. Right?
yes, the EC2 instance spin up by Carpenter, you'll pay for it. But it's the same price as any EC2 instance. No difference.
So essentially on traditional Kubernetes, there is alpha scaling, like Kubernetes will bring more nodes.
Yes.
If there is a need for that.
Yeah.
Why it's not happening here? Like how Carpenter kind of shut down the standard?
Yes, it did shut down my nodes. You know, I tested my demo yesterday, you know, shut it down. So Carpenter removed the nodes.
No, so like is Carpenter replace standard functionality of the cluster to bring more nodes?
So like in a cluster, you'll run a component called cluster autoscaler that will add or remove nodes, right?
Yeah.
So think of Carpenter as if you want a replacement of cluster autoscaler. It just works. It works a little bit differently, actually. I do have let's say a minute here. So Carpenter use what we call node pools, right? So it's a CRD. You can see here the node pools of Carpenter. So if I go get node pools in my cluster, there's two node pools, right? So you know, let's do this. Right. So in the way you define this, you know, there's the traditional thing, but the interesting aspect is you give it basically a list of requirements for the nodes that this node pools can bring. This is where it differentiates from cluster autoscaler, where cluster autoscaler, you just point it to autoscaling group and it will add or remove replicas to it. Carpenter knows a little bit more about the workloads that's pinging up, can look like the different constraint, the resource it needs, and stuff like that. You give it a little bit of requirement, right? You don't want it to use any instance in AWS. There's more than 500 of them. Some of them may not be a good fit. So you give it a couple constraints. So for example, you can control the different sizes. There's a lot of different ways to tell him. You can give it specific instance family, you know, specific amount of GPU you need or whatever, right? So this is how you actually configure Carpenter. You can also use different instance type of different architecture. For example, if you need ARM versus AMD64, this is simple 2 lines, just like here, right? I say you can use spot and on demand. You know, Carpenter will try, you know, if one doesn't work, it'll try the other one.
Yeah, thank you.
Cool. Let's see if our pods are actually running at this point. We're still in init mode. Interesting.
Are you able to configure like what to use, like priority? Because it is a site or by metric, like when they scale.
When you say priority, you're talking about
like spot or demand, there's like
so
configured, like fine tune it.
so if you configure it the way I just show up, it will prioritize spot.
Right.
Right. There's a concept of weight in the node pools, right? So if you need to do, you know, you want to make sure you have a certain amount of on-demand nodes first, you can, you know, put a higher priority on the node pools for you know, for your on-demand, then have a lower priority for the node pools of spot, for example. Does that answer your question? Yeah. All right. So it's actually, I think it's running. Let me just double check. Now it's running, right? So our job is actually running. Should take about 2 minutes for the check. So what is interesting here, it took about 5 minutes to start. And there was a question about mobile, you know, running mobile on the phone. I'm using BERT, 7 billion of nodes. This is a sizable number of gig already to download. Most, storage on phone has been improving in the last 10 years. So I cannot say how much storage we'll have in our pocket in 10 years. But right now, that will be a problem to run many of the big models that are cloned on phone. That's the reason that, how they call it, Apple private cloud, that they will send your request in the cloud somewhere. It's kind of one of the reasons, right? Is because today, device size is not able to accommodate this. Otherwise, I'm sure Apple would find a way to run it directly in the device. All right, so our job is running. So I'll let it run. I'm not sure how much time it'll take, but I do have a local copy already. So what I'll do is I'll load the last checkpoints I did yesterday. So a little bit of code, my checkpoints reside in S3. So I'm able to actually load this. It's actually, you see it's downloading the config and all the files to my local instance. And I'll be able to basically ask for specific review, right? So what I'm asking for is I want him to do a little bit of prediction using the file I just downloaded, using the pre-trained BERT base, the specific model is called case with a D. And, I'll basically tell him, let's say you receive a review like this. What can you tell me about it, right? So let's run this command. As you can see, he actually predicted that this review is a 5-star, right? If somebody says the food at this restaurant was actually wonderful, right? There's a good chance he was happy. And especially he didn't put anything, sometimes the food was great, but the service was, something else, right? Let's make this a little bit more funny, right? That's probably not a 5-star. He was not as happy as the previous customers, right? So, but at the same time, he gives us a couple of probabilities onto predictability, predicted right confidence score, right? So here, if there's specific Gen AI people that are able to translate that in English, you're welcome to do so. I will not try, right? That mess up. So, we've seen in the context of communities how, well, actually, so my job just finished. That's actually what I was going to check. What is interesting, so if I go back to my carpenter log, right, we will see, we will see that so my node pool is a little bit aggressive. Like whenever a node doesn't have anything for 30 seconds, it will delete the node. So we'll see this actually happening as I speak, right? We see the node termination, it detained the nodes to make sure there was nothing going on it, then delete the nodes, right? So those nodes are getting reclaimed by EC2. So at this point, if I do the get nodes, they're gone, right? We added 2 nodes previously. As you can see here, the 2 nodes that were 5 minutes, so 24, 174. And the other one, they're gone, right? So by using Carpenter, we were able to provision a couple nodes within 5 minutes, run actually specific training. We're not wasting any money or anything like that. Is there any other question on this? Yes. Right. So Jupyter has 2 main components. There's something called the hub, where you log in the first time, and Jupyter, kind of do get, if your user is called, my alias, for example, is Brunmat, right? It will know that it need to provision a specific space. So in my case, it's an EBS device, right? It will check, does it exist? Yes or no. Okay, I need to start a pod for that user, and it will start that in the Kubernetes cluster. right? It doesn't know about Carpenter, doesn't know anything. But at that point, Carpenter, the scheduler in the Kubernetes cluster will work just like any other Kubernetes clusters, right? If there's a place to put that pods, it will do it right away. If the pod goes to a pending state, that's where Carpenter will kick in, right? So, they don't know about each other, but they just work in kind of synergy together to optimize your clusters as much as possible. All right.
What do we need to have covered? For instance, I can create an EKS cluster.
Yes.
Let me default parameter. But then it's a lot of work to change it to start using Carpenter.
No.
This is like an array to use it.
No, Carpenter is a Helm chart you install. You do have to set up a specific IAM role, so it's able to add or remove nodes. But think of the effort of using Carpenter just the same as cluster autoscaler. It is same kind of work. If you check, we talked about data on EKS. In the blueprints, there's a ton of them that use Carpenter as well. So, if you go with those projects, it's kind of built in.
What about cost?
So we already said Carpenter is free, right? By itself, doesn't have any direct cost. But of course, you'll pay for the EC2 instance that you spin up. But it's the same price, right? If you bring them manually or through Carpenter or Cluster Autoscaler, same price, no difference. So, it consumes a little bit of resources in your cluster, right? So there's a small cost to it, yes.
Can you give it like you should not initiate more than 10 clusters, something like that? You can put a limit.
So not in terms of clusters, but yes, you can put limits inside of a node pool. So you can put a maximum amount of CPU or memory or GPUs, yes, right? So let's say you don't want your team to pay more than one GPU, right? You can put a limit of one, and Carpenter will say, my node pool is maximum capacity, so the pods will just queue until that GPU is free, right? And then the Kubernetes scheduler will decide which one is next to run, which may be interesting because it doesn't always follow a real queue. That's where Ray does a better job, because Ray really has a queue, and it keeps the order of the task, right? So when a task is done, Ray keeps a view of the resource in your cluster. So especially in terms of GPUs. So when a GPU is free, we'll launch the next task, and it keeps a queue of the task. And I'm not sure, there's maybe a way to put priorities even in your task if you have some stuff that are a little bit more important than others. Yes.
How easy it is to get GPU nodes in your cluster? Is it always available?
So this is $1 million question, right? If you need one node, there's no problem. If you need more, contact us, we'll work with you. All right, I think that's the end of my demo. I hope you learned something, or otherwise send me some comments. I see more questions, so we have time for question, or?
Sure.
All right.
So what are they show us right now?
Yes.
Is it possible to run it locally and then push it to cloud?
Yes. You have a GPU local?
Hidden source.
So, some model I'm picking up on CPU. The difference is the speed at which you'll get your answer. So there's ways to deploy with a couple different things. There's a project called OL Llama. Well, not much. You can you install it and you tell it which model you want to use. It will download Docker images running locally there at the Mac, Windows, whatever, and give you an API to locally talk to the model.
And what about data that you have to provide?
Yeah.
So is it we provide, or will it bring it itself?
So a lot of those pre-trained models already will understand most language question you can get. The funny interesting thing is always wonder how does what the model knows about the recent time, right? And we all know that Kubernetes have 3 or 4 release per year, right? So I always ask the model, what's the latest Kubernetes version of, and I gotta know where the model was last year. That's, that's one way of, because, if you ask him for something that happened last year, if he never been trained on the data, he's gonna know about that. That's also the question about why do we need to fund the model? Because this, right? If you one model, it's your community question all to, Linux 131. None of the big models knows anything about this. Like latest data point is like 128, 129 purely.
And you can to unpack as part of the project.
So, contact us, we can talk about it.
All right, so quick announcement. Thanks so much, Matt.
No problem.
If you folks like this, please go and take our survey. We really need your feedback. Matt has 3D printed Kubernetes coasters. So you need these, go ahead, give us the feedback on your way out, collect them. We have quite a few of them. Pretty cool ones for you to kind of show off with. So yeah.
I'll put some the chairs over there around the in order to all went to that side.
And this too, for those.
Yeah. Next presentation.
Thank you. Do you prefer
Hello, hello. Let me just get this up and swap displays. All right, oh, nope. Swap it back. This should be there. That should be here. There we go. Okay.
Are you sharing the right screen? Yeah, no, you're sharing on the Zoom, you're sharing. Oh, no, that's okay.
Got it?
I didn't say. You're good.
Awesome, awesome. All righty. Hi, everyone. My name is Minhal Gardezi. I am a solutions architect for Aqua Security. I've been there for about 2.5 years. So I'm both a cloud security specialist for them, as well as a solutions architect who's very invested in our product here. So I'm here to talk about one, Kubernetes turning 10. We already celebrated with the cake outside, but as well as securing the future of Kubernetes with Aqua Security. So starting out, Aqua Security, before we started out, Kubernetes started out in 2014. And we started shortly after in 2015. And as long as Kubernetes has been innovating, we've been innovating alongside them. So a couple of open source projects some of you might recognize. We have KubeBench, which we released in 2017, a Kubernetes benchmarking tool. KubeBench is actually part of the curriculum when it comes to CKA, CKS, so some of you might have used it during your time then. We have KubeBench or KubeHunter as well for Kubernetes pen testing, as well as Aqua Trivi. And I'm assuming some of you have heard of Trivi, so it's the biggest open source scanner in the world. It's the most widely used one on GitHub, and it falls under our purview. So Aqua is both an open source scanner that you can use as you want at home, as well as what powers our product and the scanning within our product. And then finally, the last open source project that we have here is Aqua, and that is our eBPF threat detection engine, looking for runtime incidents within your actual Kubernetes cluster. Now, as we move forward, once we released those open source projects, we also implemented a lot of Kubernetes assurance checks within our actual product, and that's where we introduced KSPM to the world. So obviously, we have a lot of acronyms within cloud security, but KSPM is going to be that Kubernetes Security Posture Management. So that's a term we coined. It's now used pretty widely in the market. And as we move on, as the journey with Kubernetes and Aqua grows, we coined CNAPP with Gartner. So I'm sure you guys have heard of CNAPP as well, a cloud native application protection platform. So we work closely with Gartner to term that or coin that specific term. And that's going to include both our protection of Kubernetes, as well as our dev security, as well as our cloud security posture management side. And then finally, 2021, we introduced our industry first CNDR, and that's actually leveraging our Aqua Tracy, that threat detection engine. What CNDR is a cloud native detection and response. So we'll be able to basically lift up those runtime incidents from your cloud account and give you some insight into those, as well as how to prevent those from happening. And then finally, we launched supply chain security in 2022, kind of just to round out that stack. So we have that both shift left security and that shift right security to be able to protect you and your cloud applications from development all the way into the actual production into runtime. So, and then finally, we brought that all together, like I was saying before, from the actual development into runtime. We call that our code to cloud security. And we're excited to talk about what we're going to do next with that as well. Before we go into what's next, this is a quick picture of what the Aqua stack looks like. So we're going to have that shift left security I was talking about, that dev security side. That's going to include all your supply chain security, your container image scanning, your static code analysis, IAC scanning, as well as static application security testing. But that shift right side, that cloud security piece is really where we got our bread and butter. So that cloud workload protection, that is agent-based protection of your Kubernetes workloads. So that's going to be using what we call our Aqua enforcers. So our enforcers are going to be deployed both as a daemon set on your Kubernetes clusters to cover all those deployments, as well as our Kube enforcer, which is going to be deployed at the cluster level as a container to allow for a lot of that admission control capability and being able to enforce a lot of that Kubernetes security posture management policies that we do have. And with the agent-based protection, we'll be able to enforce things like drift prevention, prevent attacks in real time. But what I really want to note on this slide is we're, one, able to secure the entire lifecycle from code to cloud, as well as the fact that we are pretty agnostic with our support in terms of the types of workloads, the types of cloud platforms, as well as even the orchestration platforms. So we can pretty much agnostically support all cloud native workloads when using the Aqua product. So what's next for Kubernetes? So we got a lot of that in the talk that we had previously. So Gen AI. So we're going to have a lot of generative AI models when it comes to implementing with Kubernetes. We're going to be seeing a lot of large language models being used within our actual development of these applications. So just to kind of see how that affects our security risk, let's talk about Gen AI applications and their risk. So this is a simple build out of a Gen AI application. It includes an LLM model. It includes your code libraries, as well as some custom code you might have written yourself. So over here, we're using LangChain. That's the framework that we're using to actually utilize Gemini, the actual large language model. And a couple of things that might be exposed here is one, as some of you may know, we already have OWASP top 10s for web applications. It's going to include things like SQL injection, but we have OWASP top 10 now for generative AI as well as LLMs. And that is going to be showing you things like prompt injection. So in this case, we'd be able to, with a very simple adjustment on how we ask questions to a language model, we'll be able to inject some Python code, let's say launch a reverse shell attack. definitely something we would want to prevent against. On top of that, we'll also have other risks, including exposure of sensitive data, maybe your open AI keys, a lot of other, basically with how speedy, how quick we can develop these AI applications, we're also introducing a lot more vectors of risk, and we're gonna wanna go ahead and secure you against those. And the way we do that here at Aqua is with our code to cloud methodology. So the way we secure the future of Kubernetes, we have Aqua code to cloud for LLMs. So starting on the shift right here, this is gonna be our agent-based workload protection, what I was talking about. So we can go ahead and block a reverse shell attack that we're seeing in runtime. But we'll also be able to track that back to the actual container scan, give you specific CVEs we're finding in that container. And then we'll track that all the way to that shift left security side and to the code repository, where we have specific checks for Gen AI, including that sensitive data exposure, that static application security testing we'll be doing, as well as being able to track it back to the specific commit that developer made that led to this cascade of issues that we're having. So we see a lot of competitors doing similar things, but what's great about this is that traceability that we have from both. Get this to it. So we have traceability to both see and stop attacks in runtime, but to be able to track it all the way back into the actual incidents we're seeing, both in the code repository level, at the container level, and at the developer level. So short and sweet, that's what we do here at Aqua Security. If you have any questions or if you want to find out more, feel free to scan this little QR code. Feel free to find me in the back as well. If you want an actual full demo of our product, I can show you how our product looks from the actual interface as well. But yeah, thank you for listening.